So yesterday we were talking about probability spaces, and we had talked about uh, the discrete event space and the we had talked about. So let's recapitulate whatever we did yesterday. So yesterday we had talked about the sample space. So let's modify the definition slightly. An abstract mathematical construct consisting of the outcomes of a random trial. This can be both discrete or depending on so the external outcomes omega are contained in this. So this is denoted by omega and the experimental outcomes are contained in this. And then we had the sigma field or the another name for that is the event space. This we define as collection of subsets of omega. Or for discrete cases, this is the power set. Right? And based on this, we had defined the probability measure. This we denoted by B. And this is a set function. A set function it maps this. Fine. And we had talked about certain properties of so these three. And we had talked about certain properties of this measure, and we had said that this omega B PR, this triad, this is called as a probability space. Now, before we discuss or before we proceed, let me consider an example. So we we have seen the example of a discrete probability space, right? So an example of a, or rather we have seen for a discrete sample space that such as the tossing coin, each outcome can be an event, or an event may contain more than so we had discussed this statement for discrete probability spaces yesterday, and I hope all of you who were listening agree with this statement. Any opposition to this statement?
So this event is an element of power set, right?
No, event is an element of power set, or the power set. We call it the event space or the sigma field.
Yeah.
Event space is slightly easier to remember, so we'll call it the event space.
Okay.
Okay, so now, but this just doesn't easily generalize to yeah, this definition does not easily generalize itself to continuous sample spaces. So for example, consider this circle, and on this circle, say this is 0, and clockwise. So let's say on this circle you have this okay, I'll use another color for this these markings. I'll use the black for marking out the outside. Yes, so this is 0, and you have a point arrowhead, and you can supposedly spin this arrowhead with a variable force, so you don't know the output, just that you know that in radians and clockwise. So the an outcome of this experiment will be that the arrowhead pointing at some location whose position from the source, or from the 0 point, will be measured in radians. Fine. So the outcome of the experiment will be that this arrowhead will point to a location in radians. Now this is an experiment with a continuous valued sample space. You guys agree with that? So this
Sir,
experiment,
actually,
yeah,
what you are trying to do?
yeah.
I lost track of what you are trying to do.
Okay, you lost track of what I'm trying to do. Consider a random experiment which involves spinning. So you have heard of that wheel of fortune or
Yes, sir.
anything like that?
Like dartboard.
Not dartboard, not dartboard. Dartboard can be an example, but we are not considering dartboard. So consider a random dial, a clock.
Okay.
Russian roulette, Pavnik, is a good example, but Russian roulette will be discretizing this thing because in a Russian roulette you can get only one out of the six outcomes. I am talking about a totally continuous case. Russian roulette, there are six possible outcomes.
Same fortune will also we have the discrete spaces only,
Yeah, you
just we
have a
rotate.
discrete space, but right now for the purpose of this discussion, consider a continuous
Okay.
space that just for a minute consider a continuous space. We'll move on to discretizing this space shortly, but right now consider a continuous space that you spin this and this arrowhead ends up on a point which you measure in radians with respect to the origin or with respect to this reference point.
Okay.
This is the random experiment. So in this case, clearly that the when the arrowhead stops, get omega. This omega is so this is a semi-closed interval 0 to 2 pi. Omega will be in this semi-closed interval 0 to 2 pi. Therefore, the sample space in this case is, oh sorry, not this. This is the sample space. Fine. Now, how would you, in this case, the question that I would ask is that how would you define an event? How would you define an event in this case? Or if I roll this needle or if I roll this wheel, let's call this
Partition the space.
huh?
So we can partition the space and call it as an event. Like whether when the needle will the needle be, what's the probability of needle being within this region to that region?
Yes. So the problem is that once you or you're right that uh, here if we talk about if we say that I bet that the phase will be pi by 8. What is the probability with which the phase will be pi by 8? Zero, because it's extremely unlikely that the needle will precisely stop at a point that is 0.125 times pi. You get people accept Shubhashish. Do you get my point? You define a point. A point is a real number with infinite precision. And the probability of this needle stopping at one precise point is zero, or the event that this will stop at one precise point is extremely unlikely. So what you can bet on is that, okay, this will stop somewhere between pi by 4 and pi by 2, or somewhere between pi by 6 and pi by 4, something like that. So in this case, an event won't be a precise outcome of the experiment, which is an so one event, one outcome is actually one outcome of this experiment is an infinite precision real number. So the outcome won't be, so an event won't, so in the continuous case, the equivalence between an event and an outcome is disturbed. So in this case, you have to define an event, or we define an event set
Sir,
of, or actually as a neighborhood.
sir,
Yeah.
sir, here also it's not just that single precise value would be problematic. For example, if we try to find a set within like 0 to pi by 2 only involving rational numbers, then also we should get a zero probability.
Yeah. So we'll come to that. Wait a minute. So in this case, we define an event as a neighborhood. So if we define the event as a neighborhood, will that take care of your problem? Or an event, this case, can be seen as a countable union of semi-closed subsets of so an event in this case is a countable union of semi-closed subsets of the sample space. So this is the mathematical definition. Obviously, you will refine this definition further if you take a graduate level course on probability, but a rough definition, or a close to precise definition of an event in a continuous space is a countable union of semi-closed subsets of the sample space. So let's dissect this definition a bit. So this means that I define an event E for the continuous space omega or continuous.
So,
Yeah.
so what's the issue in taking a complete closed subset, say 0 to pi, both sides closed?
Both sides closed is I'll come to that again. Wait about 5 minutes. Okay. So the first thing that you can see in this specific case, even our sample space is a semi-closed set. That might give you a hint. So anyway, I define an event for the continuous sample space omega as E such that E equal to union I equal to 1 to n. So this can be n tends to infinity, just that it has to be countable, and E is a subset of omega. Fine. Actually, Adit, I'll have to introduce measure or some results from measure theory to answer your question. For now, consider that this semi-closed as a part of definition of this thing. Maybe when we discuss the probability measure in slightly greater detail, the answer will become apparent to you. But let's leave this for the course on digital communication, the exact or the precise reason for this answer. Yes, so
Sir,
yeah, Subhashish, first you
so
tell me.
if we use closed sets, then there's a possibility that there would be same element within two sets.
Yeah, so that
So we can't join sets.
exactly. But here we can. Here these AI and BI may not, these sets may or may not be non-overlapping, but there exist conditions where these AIs and BIs or where these subsets have to be non-overlapping.
Yeah.
So like yesterday we discussed the probability spaces of Fi and Fj. So we discussed the properties of the probability operator or that probability measure. So those properties of the probability measure will be specified only when these satisfied only when these sets are semi-open or semi-closed. You can consider to be these to be semi-closed as well. That doesn't matter. But they have to be open on one side and closed on one side. That's all. Otherwise, you won't be able to have partitions. of this. You know what a partition is?
Yes, sir.
Okay. So the semi-openness is necessary for having partitions of the sample space. Otherwise, it's hard to have partitions of the sample space. And partitions are important for us. So so therefore, for continuous sample space, for a continuous sample space, Bhavnika, I'll come to your question in a while. For a continuous sample space, the sigma field or the event space is defined as the collection of all the events E or all the subsets of omega that satisfy fine. And also for this continuous case, yeah, our definition. General for a event E is defined as rather where f omega d omega means the is known as the probability density. F omega is the probability density function. We'll discuss about this slightly later. right now, just you might have heard about this earlier. Just keep that at the back of your mind. Bhavnik, does this answer your question? So for an infinitesimally small set, you can always have this kind of a measure, and you can obviously see that if just a second. Yeah. So this relation is okay. Now I'll answer after this. I'll answer Bhavnik's question. But is this relation okay?
Yes.
Yeah. So now look at to answer your question. Let's look at an event E that is defined as, or event E consists of A, B, this interval. Fine. Just so this is a single interval on the line. We can consider that omega is some subset of the real line containing this, containing which contains both A and B. Omega is some set of some subset of the real line that contains both A and B. Now the integral probability of E equals A to B minus fine. I'm not talking about omega as of now. So what happens in this case is, as you said, let's say B equals A plus delta. So probability of E equals A to A plus from below now for infinitesimally small case. Fine. So regardless of what the form of f omega is, this integral will be, Bhavnik, regardless of the form of f omega, what will this integral be?
Valid.
0. It's basically an integral from A to A. So the probability of a singleton event, or the probability of a singleton outcome in a continuous event space is always 0.
Sir,
Yeah.
but if I rotate this wheel,
Yeah.
I am, and when this wheel stops, this will take some value, right?
This will take some value.
And
So
that value had a probability 0.
yes,
So
yes.
how
So
how did an impossible event
Like,
occur?
no, that's not an impossible
isn't it
event.
like very
So
hard?
uh, see, there are too many. The value is infinitesimally small or close to zero, or the universe, the structure of the universe can have infinite realizations, right?
The
Uh,
best way is to compare us with the universe.
huh?
The best way is to compare us with the universe. The universe is too big for us to be considered.
Yeah. So the probability of life is an infinitesimally small event, and yet life exists. The probability that these precise combination of everything happens, distance from the nearest star, oxygen, the availability of oxygen, the availability of the exact amount of air and the value of acceleration due to gravity to have an atmosphere, all of these are necessary to have life, which is again n tends to zero, and yet we are having this conversation.
Sir, but I agree that it's a very small probability, or it's infinitesimally
Yeah,
small.
just call it delta small.
Yeah, delta small. It is
Even
delta
I
small.
find speaking that word hard. Yeah,
It is delta small, sir.
yeah.
Uh, but to say that it is zero is a very strong statement,
It's
right?
so the prior probability of a singleton event in a continuous space is zero. I have so I've shown this mathematically just now. So the probability, so you can say that in a the so or rather saying that it lies between a and a plus delta will have some probability. So assuming that this f omega is constant for omega from omega to omega plus a to a plus delta, you always say that okay, it will be close to fa dA or fa delta rather for but that delta has to be an interval. It can lie within that range. It can lie within that range. You can make this delta as small as possible, so it can be vanishingly small. As you make this delta vanishingly small, that probability vanishes. But to say that it has one precise value, so the probability of this having one precise value, so the probability of something being one followed by an infinite number of zeros is always zero. Yeah, so this is where so continuous spaces is where where probability theory starts to defy intuition slightly. I agree with that. So till now, the kind of probability that you have dealt with was mainly based on intuition. Here, as we try to deal with continuous spaces, probability and intuition at times are at loggerheads with each other. Yes, we are taking an approximation. That the probability density remains constant over that delta. So, but the point is that so like quantum mechanics, which is again probabilistic mechanics, is where physics starts to become non-intuitive. So this is our point where So we'll quantize these probabilities as we go forward. So don't worry much about that, but this is where probability is slightly, so this is a part where things are slightly non-intuitive. So now again an event space. So the probability measure on the event space for all I not equal to j, then for
Sir,
yeah.
EI intersection EJ would be 0, right?
Oh yeah,
Or
sorry. If ei intersection ej equals phi. Sorry about that. Yeah. Or equals the empty set. Now here, Adit, we have that problem because if we consider define an event as AB instead of, sorry, AB, then AIBI. Then we cannot, if some of these values overlap, then we cannot say that, or there is one common element between the two, then we cannot say that the intersection is a null set. Also, this and if
But sir, this is like adding taking the value of the limits in an integral. I mean, if
yes,
even if we take the
yeah,
boundary
so
value
it's a zero
cases,
measure set. So the singleton sets, the singleton experimental outcomes or singleton elements of omega have zero probability measure. Fine. So now let's come to Shubhashish's initial problem. Say, I know that let be the event that omega equal to I is an integer. Fine. Or rather, even why restrict ourselves to integer? I is a rational number. So we can show this, actually we can show this for integers and it's directly extendable to rational numbers. So let ei be the event that omega equals I, then fine. This is a singleton event or this is a singleton outcome. And therefore, also fine. Or rather, I should write it this way. Fine. No. So
This way of writing would be
this is incorrect.
problematic
This is incorrect. Wait a second.
because
Yeah, this is incorrect. This is correct. This is fine.
said that's also problematic.
Why?
Because if we, for example, when we'll be trying to prove it using irrationals, then
This
we'll be
is the
assuming
set of integers.
no, I can understand you're doing it for set of integers, but I'm stating that, for example, if I state that EI is the event where the pointer will reach 1 by root 2.
Yeah.
So probability of EI would be 0 during that time also. Now, instead, now if
No,
I
I
do
am
EI,
doing this just for integers. I am just doing an example.
okay,
For a singleton event, I have proved this. This is the proof for the singleton event.
yeah,
I am just saying that even if you have a countable union of singleton events,
hmm,
so this integer is a countable union of singleton events.
yeah,
So probability that omega is an integer is still 0. I'm simply saying that. And based on this, you can also extend this to the definition that probability that omega is uh, the probability that omega is a what? Yeah, probability that omega is a rational number is also 0. Fine.
So what about irrationals?
Yeah, I'm coming to that. So the real line. So let an example. Let omega let omega be the real line. Fine. So, and B, so now since we can write every singleton set as we can write every singleton set like this. So singleton sets
So
or
there's an
single,
issue.
huh?
We can't write that singleton set like this,
Why?
because this means that the left part is already, if we think it as a form of pointers, so the left part is already at A, while the right part is coming from lesser than A to A. So basically it's the notion appears to be like a mirror image of what is actually happening.
Okay, so fine.
Yeah, this makes sense.
Yeah. So we can write every singleton set like this. So because of this, so singletons along with their unions and intersections.
So this symbol also creates a problem.
Why?
So because this means that we have already, the upper bound is already at A, and we are trying to reach A, which is basically a number which is less than A from the right side.
Basically, he's trying to say this that we are trying to find a number which is greater than a but less than equal to a, which is not
Yeah.
possible.
So basically we have to assume it using open spaces only.
So we can only say it should be greater than equal to a and less than equal to a for it to be equal to a.
Yeah,
Exactly.
so
It needs to be open space.
yeah, open spaces are fine. Yes, but okay. Then how do I solve this without going into measures? That is a
So you
problem that
can
I.
do in one,
Huh?
so you can do in another way. You create the left bracket closed, and instead on the right part you give A plus delta open bracket
Limit
and
delta
make delta.
tending to 0.
Yeah.
Yeah.
Like that's how we did it in MA 101. So I
Okay.
believe that should be
Yeah. So let's do that. Delta tends to 0. Fine. So this is fine now.
so left part you
Oh,
make
sorry.
the
Yeah.
closed bracket, right
Left is
part is open.
closed. Right is open. This is fine now.
Yes, sir.
Yeah. So yeah. So we can write every singleton set like this. So singleton sets along with their unions and intersections are elements of the event space. Fine. Now from properties the event space if E is a member of the event space, then E complement is also a member of the event space. Fine. E union E complement fine. These are fine. Therefore, no, but probability that E complement. Fine. So the probability that it is irrational is 1. How do you justify that? How do you justify that?
So conceptually or mathematically?
Either is fine.
So mathematically, I've already proven in this manner. It may not be very rigorous, but it's more or less correct.
Oh, this is rigorous.
So
This is
rigorous, because rigorous would may make us do some more steps on E. But for the E complement part, it's enough.
Yes. So uh, intuitively or conceptually, how do you justify this?
So the thing is that we can within a single set of rationals, we can find between any two rational, we can find.
Yes. There are an uncountable number of irrationals.
Yeah.
Between any two rationals, and that justifies this. Fine. So we will stop here today.
So between any two rationals, there are also infinite number of rationals, right?
Yes, but between
But between any two irrational, we won't get.
but those are countable. These are uncountable.
Yeah.
Yes. So the countability is the the count, or rather countable countable unions of individual events have 0 probability. That's the key take.
Sir, again the same thing has happened that uh, if I roll the arrow, then what may take place is that a rational number would come up, but it had probability 0, and an irrational number would not come up, and it had probability 1.
Yes, so that's what I'm saying, that this is slightly different from intuition. You cannot totally follow your intuition in this case.
That actually we can use intuition if we try to make it a mapping. Like if we make it a mapping from integers to the number rationals, we can find that we will find an integer number at which it will stop, and that integer number is a mapping to a particular rational number. But in case of irrationals, it will break down, so we cannot find any
Yes,
mapping.
irrationals.
Yeah.
It'll break down for irrationals. Yes. So anyway, I think we should stop here. That is enough torture for the others, I believe, for one day. So we'll stop here and continue tomorrow.